Hi, welcome to a lecture on the Smith chart. The Smith chart's an ingenious way to graphically express a relationship between these three quantities. The impedance, Z, and the impedance is primarily what we're interested in here. And to be clear, it could be not just the impedance of a device or at a set of terminals, but the impedance along a transmission line, in which case we might say Z is a function of L, being the length of the transmission line. It relates this also to the reflection coefficient, gamma, and that too could be gamma at some point on a transmission line or for a certain length of transmission line. And then thirdly, to the voltage standing wave ratio, the VSWR. So these three things are conveniently graphically related using the Smith chart. To motivate the idea of a Smith chart, let me show you something about why it turns out to be so attractive as a way of analyzing these things. So consider the task of plotting some impedance, which I'll call Z sub L. L usually means load, but here it's just any old impedance. It's just convenient to say Z sub L here. In general, Z sub L is complex valued, and in general, it varies as a function of lots of things. The length of a transmission line could be one thing, but frequency would be a very common thing for it to be a function of. So let's consider this complex valued quantity, Z sub L, as a function of frequency. So here we're showing the real part of Z sub L as a function of frequency. And we know that the real part of an impedance can be any value between 0, for example, a short circuit, and infinity, for example, an open circuit. And it can be any value in between. So we have this infinitely large number of possible values of the real part of Z sub L. The imaginary part of Z sub L, as a function of frequency, values can range anywhere from minus infinity to plus infinity. So you can end up, and we typically do end up, with plots that look like this, where the imaginary part of the impedance shoots off to infinity, reappears down here at minus infinity, takes off again to plus infinity, and so on. So these plots are sometimes used, but they're kind of awkward. And they're awkward because it's hard to see large and small values simultaneously. It makes it harder to interpret what's going on. Secondly, this separation into the real imaginary parts is arbitrary, and it obscures potentially useful phase info. And by that I mean this impedance has phase associated with it. We chose to plot it here as real and imaginary, but we could have plotted it as magnitude and phase, and that phase would have information in it as well. Now the magnitude has the same problem, that can be anywhere between 0 and infinity, but the phase has additional information in it, and we'd sometimes like to be able to access that. So to show you this alternative way of thinking about this problem in a way that yields the Smith chart as a result, is to think about this impedance Z sub L as being a terminating impedance on some transmission line whose characteristic impedance is Z naught. And we know in this case that we will have a reflected wave in response to a wave arriving from the left, traveling to the right. And the reflection will be characterized by a reflection coefficient, gamma. And we know that this voltage reflection coefficient, gamma, can be determined from this expression. It's Z sub L minus Z sub naught over Z sub L plus Z sub naught. Now the reason I show it here is because it suggests a one-to-one relationship between Z sub L, the terminating impedance, and gamma. And that is, if we can agree on a characteristic impedance, here's Z naught, if we can agree on that value, then we can switch back and forth between gamma and Z sub L, and we'll be talking about the same thing. Now, if we switch the values of characteristic impedance, Z sub naught, at some point, this is obviously baloney. So the contract here will be that we will stick with the same value as Z sub naught throughout the analysis, and if we do that, then we'll know that any particular value of reflection coefficient corresponds to a particular value of Z sub L. And that's an enabling point in developing the Smith chart. Now, this is attractive because the magnitude of the reflection coefficient is always less than 1. So right away, we've dealt with this problem that values are shooting off to infinity and hard to plot or hard to interpret. In fact, all values of the reflection coefficient, if plotted in the complex plane, fall within a unit circle. Let me explain that with a picture. Here is the imaginary axis. Here is the real axis. So any complex number is a point in this plane. For example, 1 plus j0 is right there. 0 plus j is here. 0 minus j is here. And minus 1 plus j0 is over here. Furthermore, since the magnitude of the reflection coefficient is less than 1, then all values of the reflection coefficient fall in this circle. And that's convenient because the reflection coefficient maps 1-to-1 with the load impedance. So all load impedances can be represented as a point inside that unit circle. So let's run with this for a little while. The reflection coefficient in general is complex valued. It's given by its magnitude and a phase. And we'll write the phase here as e to the j phi sub r. Phi sub r will be the phase of the reflection coefficient. So any particular value of the reflection coefficient, say this one right here, will be given by a point, and that point will be a distance from the origin, which is equal to the magnitude of the reflection coefficient, at an angle phi sub r, which is simply the phase of the reflection coefficient. So now we can talk about three important positions in this complex plane, which we will now see is the beginnings of the Smith chart. If we have a reflection coefficient of 0, that means we're right here in the complex plane. And that also means that z sub l minus z naught over z sub l plus z naught is 0, which means that the value z sub l is equal to the characteristic impedance. So this point in the center of the complex plane, corresponding to a reflection coefficient 0, means that z sub l is equal to the characteristic impedance of that transmission line. Z sub l equals z sub naught. The second important position that you should know about is where the reflection coefficient is equal to minus 1 plus j0. This point here on the left side of the unit circle. So in that case, we know that z sub l minus z sub naught over z sub l plus z sub naught is minus 1. And right away we see that z sub l must be 0 at that point. So we refer to this, of course, as being a short circuit, or the short circuit position. The third position you should know about is this position right here on the right side of the unit circle. This is where the reflection coefficient equals plus 1 plus j0. So z sub l minus z sub naught over z sub l plus z sub naught equals plus 1. So what is that? What load impedance does that correspond to? Well, note that the limit of this expression as z sub l goes to infinity is plus 1. In other words, when z sub l becomes gigantic and positive, z naught becomes irrelevant, and the limit becomes 1. So plus 1. So this corresponds to z sub l equal to plus infinity, or going off to plus infinity, which is better known as the open circuit. So this position here on the unit circle is where reflection coefficient equals plus 1 plus j0 is the open circuit position. Now we'll see this third position here is a little bit tricky compared to the other two, but this is the first thing you need to know, is that that position there is the open circuit position. It's where z sub l goes off to plus infinity. Okay, so now if you know anything about the Smith chart, you know it has all kinds of arcs inside it, and we refer to those as resistance and reactance arcs, so let's talk about those. Now for this, the ZL notation that we've been using is going to become a little bit tedious, so now we're simply going to say Z. We know what we mean. Z is that terminating impedance in that transmission line example I showed you earlier. And in general, Z is complex valued, so it's something we can express in terms of a real part, R, an imaginary part x. And that real part you might think of as being a resistance, although it's not necessarily resistance or physical resistance. It's just the real part of the impedance. And this is typically thought of as being the reactance, although again, it's not necessarily a physical reactance. It's simply the imaginary part of the impedance. The next thing we'll do is we'll take that value z and divide it by z sub naught, and we'll call this little z. Little z is the normalized impedance. Note the normalized impedance is unitless because we're dividing ohms by ohms, so we get a unitless quantity. And this again has a real part and an imaginary part, so we'll call those little r and little x respectively. So just to make this perfectly clear, when z equals z naught, little z, the normalized impedance, is 1 plus j0. When z is 0, the normalized impedance is also 0. And when z becomes an open circuit, that is, it goes off to plus infinity, then the normalized impedance becomes plus infinity plus some unknowable reactance. So using this idea of normalized impedance, we can start to see some interesting geometry that appears within the unit circle. And this geometry I'm going to show you is something that's straightforward to derive. It's just purely math. I am going to skip over all the math here and simply show you the results. So for example, if I'm interested in the points which all have r equals 1, that have a normalized real part equal to 1, it turns out that all such points lie on this line, which is itself a circle. The left side of the circle is at the center, and the right side of the circle is at the open circuit position. Right? And you can see this is true right away, right? If I have, for example, z equals z0, then little r is going to be 1. That corresponds to that point here. But the set of all impedances having a normalized real part equal to 1 is this circle right here. Now, remember once again, over here on the right-hand side, this position is special. And in fact, it turns out that at that one point, as a limiting case, r is not equal to 1. So we have to be a little bit careful about this. Again, more on this later. You might consider what other constant values of r look like. Well, it turns out that any constant value of little r is a circle, once again. So for example, little r equals 0.5 is a circle which goes like this. Once again, its right-hand side is at the open circuit position, and its left-hand side here, in this case, is here. And if we go in the other direction, r equals 2, then the circle that corresponds to all impedances having little r equals 2 is this one here. And once again, the right side of that circle is at the open circuit position, but the left-hand side now is here. And the thing you should note at this point is that every such circle intersects the open circuit position. Now, there's one more case we can consider just in terms of the normalized resistance, and that's the case where r equals 0, where little r equals 0, the left side of that arc being the short circuit position. So if we put this all together, we get this diagram. We see that different values of normalized resistance correspond to different circles. All circles intercept the unit circle at the extreme right-hand side, and these correspond to impedances that go from 0, 0.5, 1, which intersects the bullseye, as we say, r equals 2, and then as r grows to infinity, we collapse down to that point, which we refer to as the open circuit position. But again, that's not only the open circuit position. That one point there is actually all possible values of r. All right, now lines of constant reactance as constant x. So, once again, we're in the imaginary plane. And never forget, this imaginary plane is a plane in which we're plotting the reflection coefficient. The normalized reactance corresponding to normalized reactance equals 0 falls on that line. That is, all impedances having a normalized reactance of 0 are a horizontal line going through the origin in this plot. And once again, we have this weird point on the right-hand side, so we'll set that aside for a moment. But every other point along that line inside the unit circle is a normalized reactance of 0. All points in the upper half space, that is, all points up here, have normalized reactance greater than 0. Now, a normalized reactance greater than 0, you might think of as being inductive. Now, it doesn't mean it has a physical inductance. It just means you can think of it as having the same type of impedance that an inductor would have. So it's common to see diagrams where the upper part of the Smith chart is shown with an inductor symbol. Again, all it means is that the reactance, that is the normalized reactance, is positive in the upper half space. All points in the lower half space, of course, correspond to reactances, normalized reactances, which are less than 0, which you can think of as being capacitive. So a normalized reactance equal to -1 starts here and is an arc which goes down this way. That is, any impedance with a normalized reactance equal to -1 is somewhere along that line. Just as in the top chart, any impedance having normalized reactance of +1 is somewhere along that line, which started on the right-hand side and goes up to the upper part of the chart. So if we put this all together, we see something like this. We see that all possible reactances land here on the right-hand side, but then where they go in the chart depends on their normalized reactance. X equals 0 being the horizontal line. Positive normalized reactances are all in the upper half space and form these arcs that go this way. Negative normalized reactances are arcs which go downward, and there you have it. So now if we put together all those arcs, we get the iconic image. The circles representing circles of constant normalized resistance, and the arcs representing lines of constant normalized reactance. So why do we like this chart so much? Well, let's just say it once again. This is the complex plane. In other words, this is gamma plotted in the real and imaginary axes, and every point on this chart corresponds to a particular value of gamma, and if we agree on the value of the characteristic impedance z sub naught, we can transform that into a particular impedance. And therefore, any point on this chart also corresponds to an impedance, and all such impedances are inside the chart. So this has myriad advantages when we're doing analyses in any type of radio frequency engineering analysis. And specifically, it overcomes the limitations of the Cartesian style plots that we were showing at the beginning of this lecture. It's now easy to see large and small values of the impedance simultaneously because they're all in the same unit circle. They're all confined within that unit circle. They're not shooting off to infinity. And furthermore, and something I haven't discussed yet, it reveals potentially useful phase info. Because the position of each one of these points, the phase is immediately obvious. The phase of the reflection coefficient for this point here is just that. And the phase here is just that phase. So all these phases are easy to read off the plot. So now one final comment to make in this lecture, and that's about voltage standing wave ratio. Let's think about that for a second. When the impedance is equal to the characteristic impedance, then we'll get that the magnitude of the reflection coefficient equals 0. That's reflectionless, so the voltage standing wave ratio is 1. So just based on that much, we know right away that the point at the center of the Smith chart, the origin of the real imaginary axis, is voltage standing wave ratio equal to 1. Also, we know that if the magnitude of the impedance is either 0 or infinite, then the reflection coefficient is exactly 1. Its magnitude, I should say, is exactly 1. And in that case, the voltage standing wave ratio goes off to infinity. Remember, all possible values of the voltage standing wave ratio are between 1 and infinity. So in that case, we have the unit circle itself. In other words, all possible values on the unit circle correspond to voltage standing wave ratio equal to infinity. The voltage standing wave ratio equal to infinity is a circle of radius 1, is yet another way of saying it. Now from this you could infer, and you'd be correct, that all other values of the voltage standing wave ratio correspond to circles. And in fact, you're right. For example, a voltage standing wave ratio of 3 is a circle of radius 1/2. So here is the locus of all impedances, which give you a voltage standing wave ratio of 3 with respect to the characteristic impedance. So constant values of voltage standing wave ratio correspond to concentric circles on the Smith chart, ranging from 1 at the center to infinity at the boundary of the unit circle. So once again, we've converted something which has a range which is infinite, in this case 1 to infinity, to something which is bounded and easy to visualize. Once again, an advantage of using the Smith chart for RF analysis. That concludes this lecture.